Alright, so today we're finding the area under a curve using what are called Riemann sums. Alright? We've talked a little bit about finding the area of rectangles and trapezoids in a sense. And we've had a certain number of rectangles and trapezoids that we've found the area of, and then we've added all those areas together. We've even discussed how if we made those intervals smaller and smaller and smaller, how the area of all those rectangles added together would get closer and closer and closer to the actual area under the curve. Well, now we're going to go as far to get the exact area under the curve by making those intervals smaller and smaller and smaller so it is an exact answer, okay? It's so close you'd be essentially zooming in so tiny that the area under that curve would exactly match the area of all those rectangles added together. Okay, so that's what we're going to do, kind of using Riemann sums here to help us find our area under the curve from A to B. Alright, so, and it doesn't matter if I use left endpoints or right endpoints, because as my intervals get smaller and smaller and smaller, it's not really going to matter because the intervals are so tiny, okay, that you're still going to get the exact same number. Alright? Okay. So let's just say I was using, for the time being, left endpoints for my, I'm going to use right endpoints. Okay, I'm going to use right endpoints for my drawing. So if I'm using right endpoints right here, I would be finding the area of that rectangle. And then I'd be finding the area of that rectangle. And then I'd be finding the area of that rectangle. And then the area of that rectangle. And eventually the area of that rectangle. Okay, that would be me using the right endpoints, finding the areas of all those rectangles using right endpoints and then adding those areas together. Okay? So the estimated total area would equal the sum as I goes from 1 to n of f of x sub I times delta x. And I'll explain that here a little bit. Delta x would be the base of every single rectangle, the change in x. How far x changes as I go from this x value to that x value. So each one of these would be delta x, okay? The base of each rectangle, this is in a sense our base of each rectangle. And f of x sub I would represent the height of each rectangle. For instance, when I is 1, f of x sub 1, well, here's x sub 1, f of whatever that is, wouldn't that be the height? Yeah. The value on that function there? Okay? So this part represents the height of each rectangle. So if I take f of x sub 1, that would be the height times my base. But then I do it again for f of x sub 2, so that would be the height of the next rectangle times our base, plus f of x sub 3 times our base, and so on. How's my explanation going so far? What questions do you have?
Is that just fancy way to say height and base?
Yes. It would represent every height of each one of those rectangles. Because if this is my x1 value, let's say this is the number 4, for instance, right here. If you want to know what the y value was, or in other words, the height of this rectangle when x is 4, wouldn't you just plug 4 into the function and see what you get for y to determine the height of that, kind of like you did when we broke it down with actual numbers on that graph paper? Does that make sense? So yeah, these are just random x values, okay? And the idea is eventually we're going to make these intervals smaller and smaller, but I'm drawing it big enough to where you can see it right now. Okay? So it's a fancy way of saying, okay, find the area of the first rectangle, add it to the area of the next rectangle, add it to the area of the next rectangle, and so on. We're going to sum all of the rectangles together. Okay? All right. Now, so that is our estimated total area. Okay? Delta x, how far is it? What is the width of our total area? Well, if this is x sub 0, let's just say, and this is x sub n, would you agree there are n rectangles that we'll be adding together?
Yeah.
However many that is. Okay, so how long is each interval? Delta x would equal b minus a divided by n. Because whatever b is, minus a, that tells you how far apart b and a are, right? If I subtract b minus a, that tells me how far apart they are. And I divide it by how many intervals there are, that would tell me how long each one of those intervals is. Yes, no?
Did you plug in, like, infinity in for n?
We're getting there. We're getting there. Okay? If you don't quite follow that, let me give you another example here. Okay? Clearly, right here, how long is each interval?
25.
A half, right? Okay. Well, if I wanted to know how long that was, couldn't I just take 4 minus 2 and divide it by how many intervals there are? Which would be, there's 4 of them, right? There's 1, 2, there's 4 intervals there. And you get what? 2 over 4, or 1/2. If you take the right endpoint minus the left endpoint and divide that by how many intervals there are, that would tell you how long each interval is. Is that making sense to people? Yes or no, guys?
Yeah.
We're okay. So we're okay with this.
Yeah, you cheat.
B minus a divided by n, where n represents the number of intervals, the number of rectangles, if you will. Okay? So delta x is b minus a over n. All right? And now, x sub I is going to equal a, my left endpoint, plus delta x I. So basically, x sub I is going to represent my leftmost point, and then I'm going to add 1 delta x. Then I'm going to add 2 delta x's. Then I'm going to add 3 delta x's to keep moving along and finding the different heights as I go from A all the way to B. So I'm starting at the left endpoint, A, and I'm adding a delta x I times. Okay? Adding it once, adding it twice. So far, so good. Okay? Now, clearly, this, splitting it up into these rectangles, I'm not going to be super accurate. But the more rectangles there are, the skinnier the rectangles get, the closer and closer and closer my answer is going to get to being correct, right? So what if I can make there an infinite number of rectangles there? That would be as exact as we can get. So the actual area, I can't spell, the actual area will equal the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I times delta x. Which that should look similar to the couple problems we finished class with yesterday, just finding the limit of a sum. So this is really a fancy way of saying, okay, if I split this up into infinitely number of really skinny rectangles and I add the areas of all those rectangles together, I will get the exact area under the curve. Conceptually seem all right? Okay. Should I leave this up there and work somewhere else, or should I erase? Leave it for right now? Okay. I'll go over here. You're not on film, don't worry. Alright, so we're going to find the area. How's the camera? Find the area under the curve y equals x squared plus 4 from 1 to 4 using Reimanns sums. All right, so using Reimanns sums, this is the last thing that I wrote down there. All right, we're going to find the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I times delta x. But in our case here, delta x, remember, equals b minus a over n. So in our case, that will be what?
4 minus 1 over infinity.
4, not yet. We'll leave it over n for right now, okay? We won't really plug in infinity until the very end when we find that limit, okay? So 4 minus 1 over n, which would actually be 3 over n, right? Everybody see where I'm getting those numbers from right here? Okay? And x sub I, remember, is equal to a plus delta xi. So in our case, 1 plus 3 over n times I, or I'll even think of it just as 1 plus 3i over n. Because my delta x is 3 over n. You see where I'm getting that from? What I'm doing here is I'm establishing in this function what delta x is and what x sub I is. So now I can go through and actually find the sum of all those rectangles. Alright? So, equals. I'll write the limit again. But if you just want to concentrate on the sum, that's fine. So this will be f of 1 plus 3i over n times 3 over n. All I did was replace x sub I with what it's equal to. I replaced delta x with what it is equal to. Now I'm actually going to take this and substitute it into the function. Because I'm saying f of this. Just like if I said, what's f of 5? You plug 5 in for x and see what you get for y, right? Okay? So limit as n approaches infinity of the sum as I goes from 1 to n. If I take this and I substitute it into the function, I get 1 plus 3i over n squared plus 4. All of that times 3 over n. And now it's just algebra. A lot of it. If I square this, that will require a FOIL. 1 plus 3i over n times another 1 plus 3i over n. So 1 times 1 is 1. 1 times 3i over n would be 3i over n. 3i over n times 1 would be another 3i over n. So if I got a 3i over n plus another 3i over n, that makes 6i over n.
Yeah.
Alright, that's fine. Is this still on camera up here?
No.
Okay. Here?
Yeah.
1 plus 3i over n times 1 plus 3i over n. FOIL. So 1 plus 3i over n plus 3i over n plus 9i squared over n squared. Right?
I squared is negative 1.
I squared is not negative 1 here. I like it. When you add fractions, you just add the numerators, right?
Yeah.
So 3i over n plus 3i over n is 6i over n. So 1 plus 6i over n plus 9i squared over n squared plus 4 times 3 over n. Now you got kind of a couple options. I'm probably going to distribute the 3 over n. I'm going to add the 1 and the 4 to make 5 and then distribute the 3 over n, excuse me. So limit as n goes to infinity of the sum as I goes from 1 to n. So watch closely. 1 plus 4 is 5. And 5 times 3 over n would be what? 15 over n.
1.
Again, 5 times 3 over n would be 15 over n because 5 times 3 is 15 and it's just over the n. What's 6i over n times 3 over n? 18i over n squared. And then what's 9i squared over n squared times 3 over n?
27i squared over n cubed.
Good. 27i squared over n cubed.
Yeah, you can make them all one fraction if you want to.
You could. I'm going to separate them because I think it's easier to do the sums that way. Caleb would love this, wouldn't he?
Oh. Good thing is you paid attention.
I know, that's fine. He'll appreciate the shout out.
And don't you miss Caleb.
So we're going to separate these. So if I'm going to sum 15 over n, what are we going to do with that?
Break it into 5 and 3.
Wait, so right here it looks like this is like. Is that underneath x? Like.
Oh, no. If I meant that, or if I wrote that, I'm sorry. I meant delta x times I.
Okay, that's what I was so.
Yep,
confused.
sorry. Yes.
I thought you were
Yep,
just gonna
I
try
wrote
to
it
answer the question.
too low there, I believe. That's my fault.
Okay.
So we're going to sum each of these individually. So to do 15 over n, how have we been doing that? As I goes from 1 to n. You can pull out 1 over n. I suppose you could even pull out 15 over n if you wanted to, because 15 over n is going to stay put, right? And then you just have 1 there. Either way, doesn't matter. What do you want me to do?
Just take it all.
The whole thing? Okay, so I got, sorry about this, 15 over n out in front, and then I just have 1 right there. Plus, how about the next one? What am I going to take out? 18 over n squared. And then I'd still have that I. And then 27 over n cubed. And I'd have I squared.
That's what we've been doing while I was gone.
Yep.
Okay, that's why.
Yep. What's the sum of 1 as I goes from 1 to n? N, right? Because you'd be taking 1 plus 1 plus 1 plus 1 plus 1 n times. 1 plus itself n times would be n, right?
So 15.
So I'll write it 15 over n times n, but yes, 15. Okay? Plus 18 over n squared. What's the sum of I as I goes from 1 to n? N times n plus 1 all over 2. That's one of the formulas we've memorized in the last couple days.
Alright.
Okay? Plus 27 over n cubed. The sum of the first n perfect squares. Got this one memorized?
N.
N. N plus 1.
2n plus 1.
2n plus 1.
6.
All over 6. Was that Ryan?
Yes.
Good job.
Wow. I'm supposed to say water.
Yeah. That's on film too. I'd actually give Ryan a compliment.
What'd you say about? No.
We're just talking about Stone Cold Steve Austin, right? I think he switched with him.
I don't know what's happening.
I
Okay? 15 over n times n. 15.
Yeah, did you think?
I don't even know what's going on.
So essentially here I'm just distributing the 18n to the n plus 1. So 18n squared plus 18n. All over 2n squared.
Can you take out an n, 2n?
Yeah, we'll do some things with that a little bit here.
Equals.
This I can't do in one step. I'll distribute the 27n. So that'd be 27n squared plus 27n. But I still got this 2n plus 1. I just couldn't do that all in one step. I'm going to separate these. 9 and 9 over n.
Yeah.
FOIL, 54n cubed
Plus 27n squared.
plus 27n squared plus 54n squared. That makes 81n squared.
Yeah.
And plus 27n.
And plus 27n. All over 6n cubed. Almost done, guys. We're close. Yep. (15) plus 9 over n plus 9 plus divisible by 3, 27 over 2.
Sure.
Again divisible by 3,
So
9 over 2.
squared.
Right. Now the limit of this as n goes to infinity. 15 plus 9 plus 0 plus 9 plus 0 plus 0, because those become zeros, right?
Are you always in the whole numbers then?
No.
Oh,
33 units squared.
Good thing this is going to test one.
I saw it paid.
And I leave you an entire page to work it out.
That wasn't hard, it was just I don't know what the equations are.
Yeah.